I'm Ariane from Steldt. I'm going to talk about OpenBSD's physical memory arrangements. And to start with, I'm going to tell you a bit about the theory of physical memory. Physical memory is divided into pages, and each page is usually 4 or 8K in size. And when a user space or a kernel space program runs, the virtual addresses are translated by an MMU to the actual physical pages of the packet. So it doesn't matter which page you get, because the MMU translates it anyway. Of course, this is only theory, and in practice, memory is a lot more complicated. Memory has basically 3 users in OpenBSD. There's the kernel, there are userland programs, and there are devices. Well, kernel and userland are very, very simple in this, because they have the MMU to translate everything for them, so any page will do. For this, we have a very simple allocator currently called UVM page alloc, and it just grabs a random page and gives it to us. Devices, however, are more complicated. Most devices cannot access the full memory space. This is especially a problem on 64-bit architectures, where the physical memory is a 64-bit address, so it can extend into many terabytes of memory. While the device, for example, a PCI device, can only handle 32-bit, so after 4 gigabytes, that device can't see your memory anymore. Also, devices usually cannot handle any number of pages. For the DMA, they need to program the DMA controller, which has a limited number of slots. And when those slots are exhausted, you cannot put any more pages on the DMA controller until it has finished its I/O. And most architectures, unfortunately, don't have an I/O MMU. And if they do, it's usually slow. So we cannot have the cheap translation from user space that we are normally having. So we have a bit more complicated allocator for this in the kernel called UVM pglist alloc. And it takes 5 arguments. It takes number of pages that we want. It takes the lower and upper boundary of addresses it can handle. And the alignment and boundary, which is an extra constraint that most devices have. And the number of segments. So if the DMA controller has only got 4 slots available, we can only have 4 slots, 4 segments of memory. And if we have more, then we would overflow those slots and we would not be able to do our I/O. The main classes of devices at the moment are PCI and ISA. ISA devices have an I/O range from 0 to 60 megabytes and cannot see anything beyond that. PCI devices, which are usually more modern, have a 32-bit address space and can see from 0 to 4 gigabytes. However, on an 8 gigabyte AMD64, for example, this is insufficient because half of the memory is unused, as you can see. Furthermore, we want to have some special things on our memory. We want to zero pages before we use, because those pages will get recycled. And we don't want the page that previously contained your password to end up in my programs where I can read the password and do all kinds of nasty things to your account. So we want to zero that memory as a protection measure. Also, most data structures that we use are initialized with zeros, which is very cheap if the memory is already zeroed, because we don't have to do anything. Unfortunately, zeroing memory is hideously expensive. Over 2/3 of our allocation time is spent zeroing memory. Luckily, we can have a few ideas for that. We zero memory when idle. Unfortunately, this is not yet implemented. All the books are there. We don't do it at the moment. And we only use zeroed pages when needed, which makes sense, because it's a very expensive operation, so you're only going to do it if you have to. Furthermore, we can run out of memory. And when we run out of memory, we have to wait for new memory to become available. Usually we do this by sending a signal to the page daemon to please start working. The page daemon will take memory and store it on disk. And a few milliseconds later, which is like eternity on modern hardware, we have memory available and we can run it out again. Unfortunately, when we are in interrupt context, we cannot sleep. So we cannot wait for the page daemon to do its work. So far, we have currently the allocators UVM page alloc, which is really, really fast. We have UVM pglist alloc, which, due to the way it's implemented, is really, really slow. If you double the amount of memory in your system, pglist alloc will, on average, be twice as slow. And for each of the allocators, we have a set of flags. Do we have the opportunity to wait for memory to become available or not? Do we want zeroed memory or not? So that's what's currently in OpenBSD. And it's a bit of a problem because we have to make sure that low memory stays free, so that when the device needs that memory, it's available. And the allocators are really not equipped to deal with that very well. Unfortunately, memory is still just a pool of pages. Well, actually, modern architectures also change the way that memory is presented to the operating system. So we have NUMA, which means non-uniform memory architecture, which has memory and CPUs connected in groups. And while these CPUs can access any memory in the system, memory that's local is a lot easier to access than memory that is on another CPU. Because, as you can see, if this CPU wants to access this memory, it only has to travel through one bus. But if this CPU wants to access this memory, it has to first travel to this CPU, then to that CPU, then to that CPU, and then finally arrive at memory. And more hops means that the latency for the memory access increases. So local memory is fast, remote memory is slow. So on a modern architecture, you want to exploit this to put all the memory that you're using on the same CPU as you're running on. So it's time for a new allocator, because just a bunch of pages is not working for us anymore. And this new allocator has a number of requirements. It must keep the low memory available for devices. It must be very good at contiguous allocations, because the less segments of memory you have, the faster your device can talk. And it must be a very fast allocator, because we don't want to spend eternity waiting for the pages. So that's why I wrote the mem range. The mem range splits memory into segments. So the memory from 0 to 60 megabytes is one segment. The memory from 16 to 4 gigabytes is the second segment. And the memory from 4 gigabytes to the end of your memory is the third segment. Each segment contains a counter. It tells us what number of users it has. And there are only a few segments required. My AMD in Eindhoven has 3 segments, and the NUMA machine with 8 CPUs, because of how it split the things, would have at most 10 segments. So we have the devices which eat in their own regions. We have NUMA, which has a very different view of the memory. Basically has a range for the first 2 CPUs, range for the second 2 CPUs. And if we combine that, then we get to third picture, where all the splits are connected. As you can see in this picture, the 4 GB splits from both fall in the same space. So actually this 4 GB line is split twice, but as with the rope, once it's cut, so it doesn't leave any marks. The text that unfortunately falls off the bottom, because I designed this with a bit higher resolution, are the counters. So I'll just show it here. Region 0 is used by both PCI devices and by ISA devices. So it has a use counter of 2. Because there are 2 groups of devices that make use of this. The range from 60 megabytes to 4 gigabytes, only the PCI devices need that. So it is a use count of 1. And from 4 gigabytes up to the end, has a use count of 0, because none of the devices on this machine can access it. So when the device needs memory, it will get it from a region that it can handle. And when we want user space memory, we prefer it from this region, because there it will not interfere with the devices. To make the memory fast, we have to be able to give contiguous allocations. And contiguous allocations means multiple pages in a line. For that to do, we need to actually view the memory as those ranges of free memory. So instead of putting every single page in a tree, we make 2 trees which describe those ranges. One tree is for the sizes, so that we can quickly locate the smallest free memory that our allocation will fit in. And the other tree is for addresses, so that when we free a page, that we can place it back in the right point in its tree. This helps us to keep This keeps fragmentation down, and therefore enables us to do more contiguous allocations, which is great news for devices. PMR range only has one allocator. It's called UVM PMR, get pages. As you can see, it has the same arguments that the PG list alloc in the current implementation has. It has a size, low boundary, high boundary, alignment, the boundary condition for the memory, and the flags. And when we just want any page, we can set low to 0 and high to the highest physical address that we support, and we will get the page from 2 slides back from this range, because it's the cheapest to give. When we are allocating for a device, we specify the device range, so this 0 to 4 gigabytes, and we get memory from region 1, because that's the cheapest to give out. Region 0 is considered more expensive, because also the ISA device would need it. So we don't want to touch that unless we really are required to give in this little area of memory. UVM PMR get pages has a worst case complexity of S log R, where R is the memory range, the number of ranges, so splits that I previously showed, and S is the, R is the number of free memory ranges, S is the number of segments. Usually the number of segments is a very small number, like 32 is the upper bound on both Spark 64 and AMD 64. In practice, it's much less, and I haven't seen any machines with over 3 at the moment. And the R is also a very small number because we are very aggressive in keeping fragmentation down. We have a super fast path because this method would be slower than the current allocator for any page. So if you just want any page, we have a super fast path which just grabs the page and returns it. In the worst case, it has to actually walk through all the memory and find out there's nothing available. But in the usual case, it's just get to the root of the tree and take from there, and therefore it has a complexity of 1. This allocator still honors address boundaries, so devices that only need 1 page or that don't care about the fragmentation of the pages can also make use of this. This fast path is automatically selected, so the programmer that uses this interface doesn't have to do any logic, doesn't have to do selected when there's no alignment constraint, no boundary constraint, and you want more segments than you want pages. You don't have to do any special logic. To free functions, there are 2 functions. That's basically because of the different way of looking at memory. There is a UVM PMR free pages with an S at the end, which you give a range of memory to and it frees it in one go. In the first implementation, usually the number of pages will get 1 because it is easy to integrate with the kernel. This allocator is, this free function is used to free user space memory, and it's also used at boot time to put all the memory into the free memory ranges. The average complexity of this is the log of the number of segments and the log of the number of memory fragments, because in both cases it traverses a tree, so it's a very fast free function. Then we have free page queue, which takes a list of pages, which may or may not be contiguous, and frees them in one go. This function is slightly more expensive because it groups the pages into fragments and then frees them using the same method that UVM free pages uses. So basically it has an extra complexity factor of n, which is the number of pages. For NUMA, there is currently no NUMA in the kernel. There is the PMM range can, however, be very easy to deal with NUMA because it can already split memory into segments, and therefore the only change that has to be made to it is that per CPU group there will be a different order in which to travel through these fragments, so that the local memory is always the first in this list, and the memory that's furthest away is somewhere at the end of the list. So it's very easy to adapt, and for some reason this software doesn't do. One of the nice things we can do when memory is in is to use it for mbus. Mbus are used for packets, network packets. Network packets, in 99% of all cases, they go to a network device. Very often, that is a PCI device. In other words, a device which is limited to 4 gigabytes. And furthermore, for jumbo frame support, we want these mbus to be in contiguous ranges, so that we can say to the device, please send a jumbo frame starting at this page, being 5 pages long. And the device can do it very fast. While it would have to say, please send a packet just at this page, and that page. It would have to reassemble those pages, which is very slow. And therefore, we want contiguous memory in the mbus. Because mbus are usually intended for networks, we can actually limit them to 4 gigabytes. So mbus ended in mbus pool between 60 and 4 gigabytes because of our allocator. This means that when the packet is sent to the network card, we don't have to copy it from high memory down to low memory, which is very expensive, and then send it. But instead, it's already at the right location, so we can send it in one go. ISA network devices, however, can't benefit from this, because if we wanted ISA device to benefit, then we'd be constrained for the numbers to 16 megabytes, which in modern hardware is just a bit small to fit in. But luckily, ISA devices have had the whole bouncing problem for so long that they all have their own solution. This just works. So we can afford to ignore them. The memory range is currently not yet committed. It saw light of day during C2K9, which is a couple of months ago, and it was pulled back together with quite a large amount of UVM disks shortly after. And it can't be in yet because LANDISC and HBPA are two architectures that still have trouble coping with fast page recycle. However, a lot of work is being done there, and very soon those systems will be very stable. Yeah. Any questions?
I have a question on the NUMA picture you showed where you have these 8 CPUs and various RAM sticks next to them, and sort of a complex map on how to reach one end from the other. How hard is it to get that map into code so you would know that CPU number 5 would like its own memory than number 3 or 4, but not 7, 8?
It is completely architecture dependent.
Yeah.
It's actually even CPU dependent. On AMD64, each CPU that you buy, so the chip, which may contain multiple, of course, contains a small PCI device, and we've actually got an implementation for that. It's called AMAS. It's not on by default, but that contains the memory map. It's basically what the CPU also uses to find out where to send a request for memory. And this tells us, this AMAS device tells us for each memory on which CPU it is. And also, another device on the same chip, the hyper transport controller, knows how to get from one CPU to another. To be very specific, the hyper transport controller on this CPU knows that if I want to reach upper right CPU, then I have to send the packet over there, where it will end up in the second hyper transport controller, which says, oh, you want the upper right CPU, and I select diagonally, and so on until it reaches the end CPU, where it will talk to DMA control, DDR RAM controller, memory controller, where the physical memory will be accessed and the response will be sent back using the same mechanism. The timing between that is in ACPI available, and ACPI defines an architecture-independent interface. And of course, we have to hope and pray that the ACPI table for this, the System Resource Affinity Table, or SRAT, is actually correct, as in the SRAT will say local memory has 10 time units to access, and if you want to access memory of this CPU, you will have, for example, 44 time units. However, it is the question if the BIOS implementer actually did the timings correctly, or actually even put them there, because otherwise the SRAT might give incorrect information. The other way to get it is much more complicated. It is to access the hypertransport controller and reconstruct this map with all the arrows. And once you've done that, you don't know the timings yet, you only know the number of hops, and you hope then that one hop is half as expensive as 2 hops, so that you can calculate that. or you can try and do timing. Then you really need high resolution timers, and that will be a nightmare. So basically we hope that the SRAT table in ACPI is correct.
Are the memory ranges hard-coded, or does it try to rotate if you have any ISA devices, for example, and then just divide into 2 segments if you don't have it?
There's a boot ordering problem. UVM starts first, and then one by one all the devices get detected. And somewhere on 3/4 of your boot, your ISA bus will be detected, and ISA devices. So that takes a while, and in between that, there's a whole list of devices, all want memory. So we have to make the split at ISA right at the start. And because if we don't, then the ISA range will be considered cheap, and all the devices will get into the ISA range, therefore starving the ISA devices from resources. So yeah, at boot time we have magic numbers, 60 megabytes and 4 gigabytes. We have them in the architecture dependent system.
I have a more general question. What's the roadmap for the big map support on the AMD64? Can you say something about that?
Well, AMD64 has sort of an I/O MMU. You can see it in your D message if you have BIOS configured correctly. The I/O MMU on AMD64 currently requires you to have gap memory where the I/O MMU will sit. And the I/O MMU is basically the MMU for devices. So it translates for devices to physical pages. It enables full range. It is a bit like Spark, only on AMD64 I/O MMU is very, very slow. So it's actually quite useless. So we prefer not to use it. Once the MBUS are constrained to the right area, network-wise we are big mem safe. But there is still physical disk I/O, and the disk I/O may have the same problem. The controller as PCI cannot access the high memory, so it has to bounce. And I think Bob talked about that a bit more. So basically, we need to have that safe too. And those are the 2 big systems that need to be in place before we can enable big mem on AMD64. Bigger problem is Intel, but if we have those roadblocks away for AMD64, then Intel may also work. But on AMD64, since we have the I/O MMU, if we forgot the subsystem, we can still use the I/O MMU, which helps. On Intel, we don't have the luxury because Intel is light years behind multi-computer architecture. And they only recently found out that you can actually put DRAM controllers on the chip. It will be a few more years before they discover that you can actually put an MMU between memory and I/O.
So we're not going to see that any soon?
Not for 4.7, and I don't make any predictions for 4.8. Yeah, Spark 64 is a great platform because Spark 64 has a working I/O MMU. So PMM range, it's bullshit for Spark 64 because it doesn't need it. Spark 64 just has the I/O MMU, which maps things properly, and therefore the whole question is null and void.
I'm not a kernel hacker, but I'm curious, so how does other operating systems do that on Intel CPU?
Bounce buffers. When you have high memory and you need to send to a device that has low memory, what you do is you have, at boot time, you allocate a piece of memory here, and you call it a bounce buffer. And when the memory has to happen, the I/O has to happen, you take the memory from the high area, put it in the low area, do the I/O, and then make the bounce buffer area available for the next I/O. And bounce buffers means that you copy pages all the time, because sometimes you have to copy them from memory to device and something backwards. So it's a very expensive operation. And
it also trashes your cache.
It also trashes your cache. So
which is a bigger issue.
CPU will have to reload all memory that it was working on again from physical memory. Bounce buffers are basically a fallback method only. They are not very good for actual running operating system. You don't really want to use them unless you really don't have any other options.